Hello and good morning everyone. Today inshallah I will continue with continuity for functions in several variables. This is very important topic and it depends on everything that we took from the beginning of our lectures. For all of you who didn't start yet studying, it's really very tight and hectic time for you. Our first midterm that's gonna cover all the contents till the end of this chapter. It's gonna be by the 29th or by the 29th of March, which is gonna be a Sunday. And our exam will be in this room, in the same room that we are taking our lectures in. The bottom line, you will need to understand, and will make a huge difference in studying. Number one, we started with topology. Some topological topics, you will have to go through them. Because all of the definitions involved in this part, you will face them in limits and in continuity, of course, and when we start differentiability. Are you with me, guys? So this is really very important. Once you finish this part, you will go through functions. The major thing, Miss Judy, in functions is to understand the type of the function and the limits that you will search for in order to find the domain of this function. This is really one of the basic questions that you will find in your exam. So this is number one for the functions. After functions, we did go through limits. Either you have limits from R to R or limits from Rn into R. And for limits in specific in this method, in this part, we understood in the previous lecture that we have the iterated method. And we knew that the iterated method, it's a method to prove that the limit doesn't exist. Or to elect, to give you a number, a speculation about the value of a limit. How to be sure that this value of the limit, in the limit of your function, you will have to check it using the definition. Today, I will talk with you about continuity. As I told you previously, all the resources are on Moodle, and also I've shared most of the files with you on the WhatsApp to confirm everything with you that you have all the resources. Number two, all the recorded sessions, you will find them on the YouTube. The last thing that I want to state that most of the slides, especially my slides, are between our team here and the team in Lisbon. So I made some few addition of the exercises, but it's mainly or basically covering the slides over there in Lisbon. This is a must that should be said in all times. So once more, I will talk about continuity of functions in several variables. Today's agenda will be the continuity definition, which is very important, continuous extension of a function, which is a very sensitive topic. If I have a function not defined at a certain point, I can make or not continuous. I can extend the continuity under certain circumstances. So we will take this part. Theorems of continuity, we will take several of them. And of course, the famous Weierstrass theorem and also the Bolzano's theorem, we will talk also in this part. Hopefully today I will be able to go through all of this. If I succeeded in finishing everything today, tomorrow you will be free, okay? If not, I will try to finish most of the topics today and leave tomorrow for extra practice, okay? So let's start. This is the continuity as I told you. The definition starts from here. Let f such that the domain is completely contained in Rn. We are talking about functions in several variables. Yes, you are right. It's from Rn into R, so it's a function in several variables. Okay, and the A belongs to D. So you have a point belongs to your Rn, okay, to the domain. Such that A is a limit point of D. This is a limit point of D. The function f is continuous at x equal to A, if and only if. And we are talking now about the continuity of a function at a certain point. If the limit, Judy, if the limit of f of x when x tends to A equal to f of A, which means the limit equal the definition of the function. Tell you once more, the limit equal the value of the function at certain point. تاني خلي بالك يا وسام. The limit of f of x at x tends to a مش بتساوي b, doesn't equal to b, to any value. No, it is in specific equal to f of a, which means the limit equal the definition. The limit equal the definition. Okay, we say that f is continuous in a set a completely contained in b, if and only f continuous in every point of a. So the definition of continuity at a point, that the limit equal the definition of the function at this point. And the definition for an interval, that exactly the same. The function limit already exists for all the points within the domain. So once more, Judy, this is the definition of the limit. Okay, in general, as I told you, it's functions and several variables. That's for every epsilon greater than 0. There exists delta greater than 0. Those are the radius, yes, you're right. Those are the radius of the open balls around the point in the domain and the point in the codomain, or in the range. So if I have for every epsilon greater than 0, there exists delta greater than 0, such that the delta is the radius of the open ball of x in A, which is in the domain. And if this happens, it will lead to an open ball centered at f of a with radius equal to epsilon. And in this case, it means you will have an accumulation point in the domain and an accumulation point in the codomain. The accumulation point in the domain is x tends to what? The accumulation point in the codomain, it's gonna be the limit of the function equal what? You understand what I'm saying? Of course, you are right. This is exactly the definition of the limit. But see, that's exactly the definition of the limits. These are the two definitions beneath each other. That's the definition of the continuity, and that's the definition of the limit. What's the difference between both of them? The difference is really very slight. The difference is here, f of x minus f of a. Here, it's f of x minus any point b, maybe 0 or something else. So, just as I told you, see the resemblance between the definition of the limit and the continuity definition. They are exactly the same. But in continuity, the f of x minus f of a, so it means that the limit should equal the definition. The limit should equal the definition. That's the slight difference between the definition, the limit definition, and the continuity definition. Okay, I have some theories which is by logic, which means that f and g, if they are continuous in A, which belongs to the domain of F, intersection of the domain of G, then if they added, multiplied by scalar, divided to each other, all continuous functions. So if I have a composition of two functions, of two parts, each one of them is continuous, then the result will be continuous, as you can see. Okay, the second theorem, it's about the composition. So I can get a composite function. So in case of f running from Rn into R and g running from R to R, such that f composite g, so it's gonna be a composite, it's gonna be a continuous function also. So once more, if f running from Rn into R and g is running from R into R, such that f is within the domain of f is completely contained in the domain of g, so f is continuous at A and g is continuous at f of a, which means that the composition, if it can work, because I have, if you remember, I have a condition on the composition of functions that the input functions should give an output that's capable to be used within the outer function. So if this condition works, so they can be composite from each other, then they will be continuous as the definition. Let's look to this problem. This is really a very nice example on what we did go through. Here, he wants you to verify that the following function is continuous at the origin. So all I need to know or to see that this function to be continuous at the origin, I should find out that the limit of the function when x and y tends to the origin, because it's this function, as you can see from R2 into R, should equal to the definition of the function at 0 and 0. So these two guys should equal to each other. So bottom line, I need to prove that the limit of this function exists and it is equal to 0. Look, Ms. Judy, this is the function. Everywhere except at 0. But if x, y is the origin, the value is equal to 0. So all I need, bottom line, is to prove that the limit of x and y of the function x dot len y squared plus 1 divided by the root of x squared plus y squared is equal to 0. I need to prove this. I need to be sure about this. If this happens, then this function is continuous. Okay, yes, you are right. I can split this function to be limit x and y, which is x divided by the root of x squared plus y squared times len of a y squared plus 1. Now I understood what you are saying. You need to take advantage of the squeeze theorem that we took in the previous session. This is the corollary of the squeeze theorem. Look how I'm going to do it. Yes, you are right. If I made the limit of x and y tends to the origin of this part, this means I will have a len of a 1, which is equal to 0. So the limit of this part altogether is equal to 0. Now I need to discuss the bounded or the value of the limit of this guy alone, which is x over the root of x squared plus y squared. Yes, I can smell that this function is bounded. According to the relations that we took previously, I can check that the x divided by the root of x squared plus y squared absolute is exactly equal to the absolute of x divided by the positive root of x squared plus y squared. And once we reach this point and taking advantage of the relations that we took previously, we knew that absolute of x is for sure, ya tara to remember this, Judy, the absolute of x is less than or equal the root of x squared plus y squared, which is also divided by root of x squared plus y squared. So Judy, I want you to remember that the relation that states that the absolute of x is for sure less than or equal the root of x squared plus y squared. That's one of the inequality relations that we taught previously. So once you use this relation, you will find that you have an upper bound which is 1, which means that x divided by the root of x squared plus y squared is going to be greater than or equal negative 1 greater than or equal positive 1, which means it's a bounded function, it's a bounded board, and the limit is equal to either 1 positive or 1 negative. So according to the corollary, this is a bounded value. According to the squeeze theory and the corollary related to the squeeze theory of limits, now I can find that the limit of x and y tends to 0 and 0 for x times len of y squared plus 1 divided by the root of x squared plus y squared is exactly like the limit of x and y tends to the origin. The x over root xy plus x squared y squared is bounded less than or equal 1, where the len of y squared plus 1 is limited to 0, and 0 times anything is equal to 0. Now I have that the limit is equal to 0, and at the same time the limit of the function, the value of the function, so that's the limit, which equal to f at 0 and 0 is equal to 0. So the definition equal the value of the limit. Hence, this function is continuous at the origin. This is how to solve this problem. Let me do it with you again once more on the screen. Let's go through it again on the screen. So once more, I have the function with me, which is running from R2 into R, as you can see. And let's go through it step by step. So the first step, as you can see, we must prove that the limit is existence equal to 0. This is gonna be really very easy by splitting x over root x squared y squared, okay? And times len y squared plus 1. This guy, you will have no problems with this one. Why you will have no problems? Because the denominator is equal to 1, so all I have to do is to substitute, and this value, or this part, is gonna equal to 0. For the other part, which is x divided by the root of x squared plus y squared, it's really very easy to prove that this guy is bounded. How to use this? To take an advantage of this substitution, that an absolute of x is less than or equal to the root of x squared plus y squared. Once you reach this point, you will be able to eliminate these two guys together, and you will have now this part is bounded, while the other part is equal to 0. So 0 times anything, then the result will be 0. And that's a consequence of the corollary of the squeeze theory. I've wrote everything for you as the slides. So now I have the value of the limit is equal to the definition, to the function is continuous at the origin. Now I want to use advantage of this specific problem to be able to extend the continuity in the cases of having functions not continuous at certain points. So look to this definition. Let f is defined from Rn to R be a continuous function on its domain, and let A be a limit of point D such that A doesn't belong to the D. What's that mean, Ms. Judy? That means in f is continuous within this domain, but is not continuous at A, okay? Or A doesn't belong to this domain. So the function is defined within the domain. And you have another point, which is A. The function is not belong to your domain. I can extend the continuity to this point. How to extend the continuity of this point? If the limit of x tends to f of x exists in R, then we can define a continuous extension, making an update in the function. I will improve my function, that I will make it covering the main definition plus the definition of the limit. So I can extend it on this condition. So I will change the shape of the function Judy. This part is the general function which is defined on J. But A doesn't belong to this domain. So in this case, I will have to put the value of the limit equal the function. So in this, exactly like the previous example. Exactly like the previous example. And this is how we can extend the continuity of a certain function. Let's look to this problem. It's a very nice problem. Okay, بص على دي كده جولي. We will consider the continuous function f from R2 except 0. يبقى it is from R2 into R, but it doesn't pass through the origin. Okay, and it is defined by, look to the definition of the function. Look to the definition of the function. It is sine x squared plus y squared divided by x squared plus y squared. So this function is defined everywhere, but it's not defined at the origin. Am I right or wrong? Because if you make a substitution, you will find 0, sine 0 is 0, divided by 0. So 0 by 0 is not defined. So it is defined on all the domain, but not at the origin. I will try to extend the continuity of this function to the origin. شوف يا عمرو. The first step that I will do, in order to make this function extendable to the origin, all I have to do, to know that I'm searching for a new function. My new function should be sine of an x squared plus y squared divided by x squared plus y squared, where x and y belongs to the whole domain, or x and y doesn't equal to the origin. صح؟ طيب, when x and y is equal to the origin, I should find some value here that will make the limit equal to the function, if it exists. Okay, we can do this simply by trying to find the limit of x and y of the function sine x squared plus y squared divided by x squared plus y squared, as you can see. If I make a substitution, so in x, y tends to the origin, I will have 0 over 0. And, oh, wait. Well, you are right. This is remind me by the famous problems at z equal to 0 of a sine z over z, which is equal to 1. That's one of the famous values of the limits. Sine x over x, when x tends to 0 is equal to 1. Now, I can take advantage from this point. Because now I know that the limit of this function is equal to 1. So in order to get a new function which is continuous at the origin, all I have to do is to insert this guy should equal to 1. So the function in everywhere, it is sine x squared plus y squared divided by x squared plus y squared. But once it is near the origin, it should be equal to 1, as you can see. So once more, I can do all of this once more. So here we go. This is my main function, which is sine x squared plus y squared over x squared plus y squared. If you make the substitution, it will be 0 over 0. So the result should be equal to 1. So all I have to do is either to replace these two values, x squared, y squared, by z. Now I'm dealing with sine z over z, which is, of course, you know that's gonna be equal to 1. Now I have the limit of the function at the origin. So all I have to do is just write f can be extended by continuity to the origin 0 and 0. And the continuous extension function can be, this is the function on the first wing of your function, and that's the limit. So for everywhere where x, y doesn't equal to the origin, that's the main function. When your function equal to the origin, then the limit should equal to 1, as you can see. Now I've extended the continuity of the function till to the point 0, 0, as you can see. And that's a classical problem. You may have exactly this problem over and over again in your exams. Now I will go to some of the important theories relative to continuity. The first of them, a set K is a subset of Rn. It's a compact set. What's the meaning of compact set? If you remember from the first slides, that the first part of our lectures, when we spoke about topology, and we talk about the various relations connecting the interior and exterior of a certain region or a set, we spoke about this part, which is the compact sets. The compact sets are those types of sets where two conditions are met. First of all, it is a bounded set. Second, it is a closed set. So for those types of sets, they should satisfy the two conditions. They are bounded and closed, as you can see. Okay, very good. So a set K belongs to Rn is a compact set if K is closed and bounded. Weierstrass theorem, which is really a very important theorem, states that if K, your set, is a compact set, and the f is a continuous function all over your set, then f has a maximum and a minimum. And that's an entrance, small entrance, to the next stage in our course, to the optimality search. So this is really very important part, should be introduced right now. So that's Mr. Karl Weierstrass, who lived between the 1815 and the 1897. Weierstrass, according to his theorem, states that if I have D from Rn into R, it's a continuous in a compact set, of its domain, then F has a global maximum and a global minimum. The most two figures that's really tempting for understanding Karl Weierstrass, if your domain or your set is a compact set and it is bounded, then within this set you can find a maximum and the minimum, as you can see. And this is also another case for the application of Weierstrass, as you can see. Of course, if your function breaks any of the main conditions, it's a compact set, which means it's a closed and bounded, then we cannot be sure about the application. So if you look to this set, for example, which is running from A and B, and it has open balls, or the ends are not with you, so it's not bounded, Weierstrass theorem cannot be applied. So A and B is not a compact set. We cannot apply the Weierstrass extreme value theorem to H in this set, and in this case we can do it. Also, one of the challenges is your set should be continuous. So if A and B is compact set, but J is not continuous, if the function is the function is not continuous within your interval, then therefore we cannot apply also Weierstrass theorem. So if you look to this interval, which is compact set and bounded, but it is not continuous, we cannot apply Weierstrass theory also. J doesn't have a global maximum or minimum, as you can see. W is a continuous in a compact set, okay? And so, applying the Weierstrass extreme value theorem, we conclude that W have a global minimum and a global maximum. That's the case if I'm talking about from Rn into R, or for functions in several variables. According to the definition, if it is compact and the function is continuous, then I will have a global maximum, as you can see, or a global minimum. And we spoke about this in the previous session, that if I have functions depend on two variables, then the function will be in 3 dimensions. What I mean is, this function is running from R2 into R, which is function in several variables, so it is in the 3 dimension. This is why you can see those are the R2, X and Y, and the results is represented on the third dime, or on the third variable, which is the range, of course. So that's mainly the Weierstrass theory, and it's really very beneficial. We will see how we will use it in examples just in the coming slides. Let's look to this problem. He wants you to consider the function f, which is defined by x squared plus y squared plus e to the power of x squared plus y squared. As you can see, this function, it consists of two parts. The first part is a polynomial. The second part is an exponential function. And he wants you to consider set A, where this function is applicable on, which is x squared, xy belongs to R2, when x squared, y squared less than or equal to 1. That's the domain, which is the unit circle. So all I have to do now, in order to check the compactness of this set, is to be sure that it is closed and bounded. So in order to be sure that it is closed, this is really very simple. As you can see, we are talking about x squared plus y squared less than or equal to 1. So we are talking about unit circle, where the boundary of your circle is already determined by the circle itself, so it is closed. And for this function to be bounded, yes, it can be bounded, because I can't simply find an open ball centered at the origin, let's say with radius equal to 4 or to 5 or to 6, and it will be an upper bound for all the values in your set. So yes, your function, your set is closed as the boundary already defined, and also bounded, and there is an open ball that contains a, for example, xy such that x squared plus y squared is less than 4. It's an open ball centered at the origin, and it can be contained. So it's a compact set. Okay, can you justify that f has a maximum or minimum? According to Weierstrass theory, since it is continuous function and the set is compact, which means closed and bounded, then we will have a maximum and the minimum according to Weierstrass. The last thing, can we determine m and n? Yes, of course, because as you can see, for this circle, or for this region, I have two major points, the point at 0 and 0 and the point at 0 and 1. So if I want xy belongs to A, the general region is x squared plus y squared is between less than or equal 1, greater than or equal to 0. This will happen, the 0 will happen at the origin, and the 1 will happen at the end of your circle, which is 0 and 1, 0, negative 2, or 1 and 0, or negative 1 and 0. Those are the four corners. So if I want to get the range of this value, or the boundary, or the limit value, in order to know which is maximum and what is minimum, I will start from the limitation, which is x squared plus y squared less than or equal 1, greater than or equal to 0, and then I will add e x squared plus y squared on both sides. If I added on the 3, so let's do it step by step. If I have, now I have x squared y squared, which is bounded by between the values of 0 and positive 1. I need to make this function to be here. So all I have to do is to add e to the power of x squared plus y squared to the three parts of the inequality. So now I will have e to the power of 0 to the power of 2 plus 0 to the power of 2 less than or equal x squared plus y squared plus e to the power of x squared plus y squared, which is the function less than or equal 1, then plus e to the power. Let's say I will use the point 0 and 1. So it's going to be 0 and 1. So the limitation of this function f of xy, it is 1 and 1 plus e, as you can see. I will take 1 plus e at the maximum because it's the higher value, and 1 as the minimum. So for this function, or on the interval of the domain, which is the unit circle, okay, which is the unit circle, we succeeded, as you can see, in finding the value. So just in a second. Okay, so once more, as I told you, so m equal to 1 and f searches for this value at the origin, and the maximum, which is m capital, 1 plus e, and it will happen at the boundary of your line circle, as you can see. This question, by this part, it's one of the major problems that you may face down the road for problems within exactly problems that may appear to you down the road. Okay, once more, this is the in this part I want to define the arc-connected sets. I may have sets which are arc-connected, and the arc-connected sets is defined as the following. A set A, which is completely contained in Rn, is arc-connected if and only if every x and y belongs to A exists a continuous path in A that connects these 2 points, that there exists a continuous pi gamma such that from 0 to 1, which leads to A is completely contained in Rn such that gamma 0 is equal to x and gamma 1 is equal to y. Bottom line, I can connect the points inside the region with an arc, or with a general definition of an arc, and it will be connected. So for this one, for this disk, or for this ring, I can connect any x and y by a certain curve without going out my region. So yes, it is arc-connected. For this one too, it's arc-connected also, because each one in the first square can be connected to the origin, and the origin can be connected to each point in the other square. But this guy, no, it's not arc-connected, because they are already in two separate first quarter, third quarter, and the connection between both of them doesn't belong to yourself. So no, it is not belonging, it's not an arc-connected. I've also wrote the definitions for you in the PDF, which is, this is an Arrhenius ring, which is, the ring is continuous in any 2 points in the ring can be joined by a curve inside that, for example, moving around the circle. Number B, the two squares touch each other at the origin, so simply I can move to any point, as I told you, explained to you, through the origin. So yes, it's a continuous path. But for the third one, due to that the origin doesn't belong to your domain, I'm not going to be able to do it or to move from the first square to the second square. So here the point 0, 0 is removed, shown as open. All the two squares meet only at that missing point. Since the connection point is not included, there is no connection between these two sets. Now we come to the last part of our lecture today, which is the Bolzano's theorem, which states that for let A is a subset of Rn, be an arc connected, and let's set and let F be a continuous real function in A if x and y belongs to A, such that f of x is less than fy, then for every k belongs to this interval, there exists C belongs to A, where f of C is equal to k. So once more, the definition is really very important, which states that for every k, so for every k, okay, belongs to the set of f of x and f of y. So k belongs to the range or the codomain of this function. There exists C belongs to A, so there is a point within the domain of where f at this point will equal to k, which belongs to the f of x and fy. It's an I feel I give you the hint, the feeling of the mean value theory. Okay, so once more, let's use Bolzano's theorem to justify the range of f is m into m, and this is really very simple. The set A is a connected set, as any 2 points of A can be connected by a continuous path. So f is continuous in A. So by Bolzano's theorems, we can conclude that f takes all real values between the minimum and the maximum. Therefore, the range of f is 1 and 1 plus E. There exists this range. That's an exercise, a standard one, on all what we did go through. So if you remark, he's stating here, let f be two variable real functions, continuous in the set of A, where xy belongs to R2, and such that the absolute of y is less than or equal to x squared, and x squared plus y squared is less than or equal to 1. Which means that for this guy, I will have absolute of y is less than or equal to x squared, which is positive